let's talk about what causes changes in rotational motion. So this starts with this picture. Okay. So we go bowling ball rolls down the lane, right? Hit the pins. What do the pins start doing? They start moving, okay? But they actually start moving in two ways, right? Which way do they move? Okay, so they move like backwards, outwards, and stuff like that, okay? Linearly. But what do a lot of them start doing? With this. Okay, flipping, right? Which, if we use big science words, we would say that it is now rotating, right? So these pins are actually engaging in two kinds of motion, both linear, or what we refer to in big people words as translational motion, and rotational motion. Okay? Look at all these new words you have. If you bust out translational motion in conversation, it's going to score you some points. So just throwing that out there.
That's not a ball.
Luke, is that a question for you? Okay.
No.
This is actually a picture of a hammer being thrown through the air, which I would...
Where'd you get bowling pins?
Those little white things.
Which
Yeah, but it's
I would like to point out, I don't recommend throwing a hammer through the air, okay, for safety purposes. Okay. But a time-lapse photograph, or I guess a stop motion photograph, whatever, of this hammer. But you can see that the hammer moves through space. Okay. More specifically, what kind of path is it taking? Parabolic, because it's what, Luke? Is a projectile, okay? But, Luke, as far as anybody knows on the recording, you said that. So, I'll just leave it at that. So, but as it's moving through space in a projectile path, right, a parabolic projectile path, what else is it doing? Spinning or rotating. The translational motion is the parabolic one. Okay? Translational motion is moving through space. That's translational motion. But they also spin around a point in space, and that's rotational motion. Okay? Are we okay with that? Lost my train of thought.
Okay, she's confused. No, she has the translational and rotational one at the same.
Okay. So, no. Okay.
Sorry.
That's okay. Moving through space, right, that's translational motion. Okay? Even if this...
Wait, like, can you give me, like, an example?
Sure. Okay? If we go back to an example that we sort of used when we introduced this stuff, okay? The Earth moving in its orbit around the sun, that's translational motion. It's moving through space. Does that make sense? But the Earth spinning on its axis to create day and night, that's rotational motion. Does that make sense?
Oh, because it has, like, a point.
Right. It's rotating around an axis, but the same thing with the Earth. The Earth does this as well. It has translational motion because it's moving through space in its orbit, but it also has rotational motion as it moves around an axis. Does that make sense?
Yeah.
Okay. All right. We talked about rotational motion, but the rotational motion, at least the last problem we did, which was actually a good transition, and I didn't actually think of this, but the last problem we did talked about an acceleration, a change in rotational motion. Oops. Yeah. Sorry. You are right next to the microphone after all.
I forget some things.
This object is rotating through space, but as it's rotating through space, it's actually slowing down, just like the wheel was, right? Something has to cause that, okay? Let's not go through here. And that thing is torque, okay? Torque causes changes in rotational motion, okay? Or it causes angular acceleration. see if we can make some connections here, all right? Theta was angular displacement, similar to regular displacement in telling us how much of a circle have we rotated around, right? Omega was angular velocity, right? How fast are we actually spinning? Sorry, I should do this. Theta, angular displacement. How far do we spin? Omega, angular velocity. How fast are we spinning? Alpha, angular acceleration. How much are we changing? Torque is causing the change in rotational motion. What is that similar to a concept that we've talked about all year long? Gravity is a specific type of a force. So torque we sometimes refer to as the rotational equivalent of force. Okay? Torque causes things to change what they're doing rotationally. Okay? That's what force does translationally. Force causes things to change what they're doing translationally, or in space. Okay? Does that make sense? Kind of, sort of. Go ahead.
So like if you throw a baseball, what costs 6 minutes, or like what curveball?
Sure. Yes. Your fingers would actually be doing two things to that ball. Okay? They're applying a translational force because they're moving it forward. Okay? But the friction between your fingers and the ball are applying a torque and causing it to spin as well.
Friction is a force too, so
Sure.
is torque like the result of the force?
Yes. Hold on. Good transition. So, absolutely. Torque depends on a force being applied to the object, but also the distance from the center of rotation. And those are two big concepts. Okay? We'll talk about that in just a second. So yes. Dr. Bill. Because you asked, you can do the demonstration. So, see point A.
Yeah.
Just put your finger on there and spin the wheel. Okay? Now put your finger at point B and spin the wheel. Harder, easier? It was harder. Okay? It's harder the closer we are to the center. Alright? And there's a reason for that, which we'll talk about in just a second. So, you see, like, the wheel spinning demonstration, two things. One, you have to apply force, right? But depending on where we apply that force to the wheel, it makes it harder, easier to spin, right? If you really want to spin this wheel, right, where's the best place to spin it? Right? That's pretty easy to do, okay? All right, let's talk about why. So, formula for torque. First, new Greek letter, everybody. I know, it's exciting.
What's that?
That is a Greek letter tau. It's a lowercase tau, and I usually draw mine like this. Okay? It's like a curvy T. Kind of like half pie, I guess. So yeah, so without the other leg. So, yeah, usually
Just a slice of.
go for it if you're just going fast. You kind of give it some of this. Okay, you don't have to do the curvy part at the top. Okay?
Do
But-
make it fancy.
Torque depends on the force we apply, the distance from the center, and then there's some angle component, right? Meaning probably we're dealing back with what? Component vectors of some kind, all right? Although having this in the formula takes care of the component vector that we actually need, so you don't actually have to figure it out. Okay? So T, or the tau, stands for torque. Okay? F stands for the force we're actually applying. D is something that we refer to as the lever arm, the distance from the center of rotation to the point where the force is being applied. So if we go back to the wheel, right, what would we say about the lever arm for point A versus point B? larger lever arm, right? Meaning that if we put a larger value for D in this equation, right, how much torque are we going to get out of it? More torque. What kind of relationship? Direct relationship. Okay? Then theta is the angle between the applied force and the lever arm, which sounds confusing when we're just writing it down, but when we start looking at some pictures, we'll see why or how that looks. Seth, I'll move the spike wheel for you so you can finish writing those notes down. I don't want you to miss the bottom of the screen. That's good. That's for the recording. So if you know if your mom starts getting on your case and you're like, Mom, I'm listening to the recording, I was taking notes. Just make sure you pause it before this part. Alright, so. Give me a little shout out here, a little love. Alright, so unit for torque, newtons times meters, okay? That just follows along with the units in here. No fancy name for it, no torques or... N times M, which you can write as NM, but usually we put the dot in between them.
It's okay, that's what you're
Torque is unit N times.
Alright, so if we talk about this wrench, okay? Torque, a torque wrench. Torque, this is just how font, I believe this is Arial font on the computer, it's how Arial font writes tau, okay, but it's tau. It's equal to F times D times sine of theta, right? So here's our F, okay, the actual force that we're applying. Here's our D, in this case, the distance from the center of rotation. In this case, it's just going to be the length of the wrench, okay? And then we look at sine theta, okay? There's F, there's D, okay? Then theta is the angle between the force and the lever arm, okay? Which is not that, okay? I know it's confusing because of that picture, but that's not theta. This is theta. That's the angle between the force and the lever arm. Does that make sense? Okay? A lot of times, especially when we're talking about torque, at least to begin with, we end up with a value greater than 90. Sorry, lost the train of thought. A lot of times we end up with a value greater than 90, which is okay. We can still take sine of those angles. But what does that do for us? Okay? Not all forces will produce torque. Okay? Luke, push inwards towards the middle. Any torque?
No.
Did you apply a force?
Little one.
Okay, you applied a force though, right? Okay. Was there a lever arm?
No.
Was there a distance from the center of rotation that you applied the force?
Yeah.
Yeah, okay. But how did you apply the force?
Straight up.
Straight on, right? You applied it towards where?
Center.
Towards the center, and that's the problem, okay? Let's finish up this screen, we'll be done. Only forces that are perpendicular to the lever arm will produce torque. Forces parallel to the lever arm, or forces that pass through the center of rotation, will produce no torque.
Use a torque wrench for going outside the wheels.
Yeah.
Take it to top.
Does it have to be exactly perpendicular?
Yes, and that's what the sine theta does in the
Why?
Say again. It's the Y value a lot of times if we're dealing with angles that are less than 90, but we're dealing with greater than 90, it's just the one that's perpendicular to the lever arm. Okay? And that's where you have to be careful with theta, which theta you're actually dealing with. Okay. So this is basically what Luke just did. He just pushed from this direction. He pushed like on the end of the wrench, okay?